A time series can switch behavior without labeling the switch. A Gaussian HMM in hmmlearn infers those hidden regimes and decodes when each state was active. You'll see how to connect the pieces into a workflow that learns behavior patterns and labels the active regime at each time step. I'm Professor Pi, teaching AI foundations with simple Python. Time series data often hides a few discrete modes. Think of market returns that sit quietly for a while, then flip into a spiky volatile patch, or server latency that jumps whenever a background job kicks off. A Gaussian hidden Markov model is a compact, interpretable way to surface those modes and produce a decoded timeline you can inspect or feed into later analysis. It works well on modest datasets and gives a clear segmentation to reason about. A helpful picture is a machine moving between a few rooms, where each room plays its own number soundtrack. You only hear the sounds, not the room labels. The Gaussian HMM learns each room's sound pattern and the rules for moving between rooms, then gives you the most likely room sequence behind the sounds. The upside is simplicity and a readable timeline. The downside is you must pick the number of states and accept the Gaussian noise assumption. We will build a tiny example that demonstrates the full loop. You will see how to create a short observed sequence, fit a two-state model, compare 1 versus 2 states, name the learned states as low and high regimes, and then decode the timeline. That gives a minimal but complete workflow you can scale later. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a tiny observed sequence to show the mechanics. This snippet creates the tiny time series input X that the HMM will learn from. The hidden states are not labeled, so the model only sees a sequence of observed returns in X. Each observation is wrapped as a one-item list because Gaussian hidden Markov models expect rows of features even for a single feature. Repeating those returns gives us enough points to fit a simple model without cluttering the screen. The printed output confirms the number of time steps and the return range, which grounds the regime detection task in actual values. That gave us a clean X to work with, but we still need the model to find patterns. Next, we fit a two-state Gaussian HMM so we can see separate regimes. This example fits a two-state Gaussian HMM from hmmlearn to the observed sequence. The call model.fit estimates both the hidden transition behavior and the Gaussian emission parameters for each latent state. N components equals 2 tells the model to look for two regimes. Covariance type equals diag keeps the variance structure simple for this single feature example. And NITIR controls how many EM iterations hmmlearn may run. More iterations can help convergence, fewer makes training faster. The printed means give the first concrete hint that the states separate lower and higher returns. Fitting a model is useful, but we should at least check whether one state or two states better explains the data. That comparison guides whether regime structure is actually present. This code compares whether one hidden state or two hidden states explains X better under hmmlearn. A one-state model treats the whole sequence as a single behavior, while a two-state model can split lower return and higher return periods. Each candidate is trained with candidate.fit X. Then candidate.score X returns the log likelihood of X under that fitted model. Remember, this is a simple training set comparison, fine for demonstration, but not a full model selection protocol. The output picks the stronger candidate here, which lets us focus on the more useful regime structure for the rest of the walkthrough. The model learned numeric state labels. But those labels are arbitrary. We should map them to human-friendly names, so decoding becomes meaningful when we talk about results. This snippet gives the hidden states human-readable names after hmmlearn has learned them. State numbers like 0 and 1 are arbitrary, so we order them with np-argsort model.means.ravel, and then map the smaller mean to low and the larger mean to high via state name. That small naming step avoids the common trap of assuming state 0 always means low or high. The output shows the named regime means, which makes the learned states easier to discuss before we decode the full timeline. Now we decode the full timeline to see when the model believes each regime was active and to get a compact summary of switches. This example uses model.predict x from hmmlearn to decode the most likely hidden regime at every time step. Under the default Viterbi behavior, predict returns a single best path for the whole sequence rather than independent labels per step. Named path converts those numeric states into the readable names we set earlier, so the decoded timeline is straightforward to inspect. Switches counts how often the decoded regime changes between consecutive steps, giving a concise summary of the segmentation. The printed preview of the first decoded regimes and the switch count completes a tiny baseline for time series regime detection. You can map this toy example to a real project by replacing the tiny x with daily returns for an index like SPY. The same flow scales. Build observations, fit candidate models, compare component counts, name states, and decode. On larger datasets, you'll spend more time on model selection and stability checks. It is a probabilistic time series model that assumes discrete hidden regimes and Gaussian emissions. Use it when you suspect a series alternates between a few distinct behaviors and you want a decoded timeline. One caveat is that the number of states and the Gaussian assumption strongly shape what you find. So validate with different settings and domain checks. Try fitting with different n components on a longer dataset. For example, 3 components on daily SPY returns, and compare the fitted means and the decoded timelines. That often reveals finer-grained regimes, or shows that extra states only split noise. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.